Okay, good afternoon, everybody. So we stay as the volatile elements, but now move to more isotope geochemistry. So the project was to measure selenium isotopes in different solar system materials and to constrain the origin and a possible later addition of volatile elements to the Earth. I would like to start with a sketch from the protoplanetary disk. So at the protoplanetary disk, we had a temperature gradient with hot temperatures in the center and colder temperatures in the outer areas. And this temperature gradient mainly influenced the condensation of elements from the solar nebula. So we had the condensation of refractory elements in the center of our protoplanetary disk, while the volatile elements stay vaporized. And we had the condensation of all elements in the outer areas of our solar system. And this can be also nicely seen if we analyze carbonaceous chondrites for the element abundances. This is shown on the next slide here. Here you can see element abundances normalized to the bulk solar system composition as a function of the condensation temperature. And what you can nicely see is that we have a nice trend at the moderately volatile elements with decreasing element abundances with decreasing condensation temperatures. And so the abundance of all these elements is independent of their geochemical character. So for this study, we will study the element selenium, which has a very low condensation temperature of about 700 Kelvin, to constrain the origin and addition or possible addition of volatile elements to the Earth. From the low condensation temperature, we would expect that the initial selenium concentration in the Earth was very low because it may not be fully condensed from the solar nebula. Selenium has 6 natural occurring isotopes from mass 74 to 82, so this gives us a relative mass difference of about 10%. And we studied the selenium isotope composition in different meteorites, so I indicated the samples which we measured so far in red. So from that we have the selenium isotopes and the concentration data. And for one Martian sample, we so far just have just the selenium concentration. We measured bulk meteorite samples, digested them, and measured them with a double spike approach for selenium isotopes. We measured the selenium isotope composition in 2 different lab standards to control the precision and accuracy of our method. From the upper diagram, you can see that we measured the selenium isotope composition of the MH495 selenium standard solution. And although we are not the most precise, we get not the most precise data, we are more or less accurate. So our results of -3 plus minus 0.25 per mil fits very well to previous measurements on this solution. And we also measured the selenium isotope composition of a Green River shale obtained from USGS. And the value of 0.06 per mil also fits quite well to previous measurements. We take the uncertainty of this lab standard, or this rock standard of 0.43 per mil as a representative for the uncertainty on our meteorite samples. So coming back to more introduction slides, here you can see element abundances of moderately volatile elements in different chondrite and meteorite groups, as also from the Earth's mantle. And there are 2 nice things on this picture. What you can see is that the CI group of the carbonaceous chondrites most closely fits the element abundances of the bulk solar system, and that all other chondrites are depleted in selenium concentrations by a factor of up to 5. And this depletion of elements depends on the condensation temperature. So we have more depletion for zinc, which has a very low condensation temperature, than for manganese and sodium. If you now look at the Earth's mantle, which is shown on the uppermost right here, you can see that the trends we can see here qualitatively fits the carbonaceous chondrites in having depletions of manganese and sodium and also in zinc. But what we also observe is that the selenium concentration in the Earth's mantle is extremely low. And this is because selenium is not only a chalcophile element, but also a siderophile element. That means that a large portion of selenium is sitting in the Earth's core, and that explains the low concentrations in the Earth's mantle. If we just focus on element concentrations in the Earth's mantle, I will show you a slide which Chris showed you just before. So you can see element abundances also normalized to CI of the lithophile elements, also as a function of condensation temperature. And you can see that elements with a condensation temperature below 1,300 degrees are depleted in the Earth's mantle because of their volatile character. If we now look at the siderophile elements, we can see that they are depleted in the Earth's mantle just because a large fraction of them is partitioned into the Earth's core. And the chalcophile elements are quite hard to characterize, but you can see that some of them are extending the trend from the lithophile elements here, but there are 3 elements which are highly depleted in the Earth's mantle, that is selenium, tellurium, and sulfur. And these are even more depleted in the Earth's mantle than the highly siderophile elements, so the platinum group elements. Now I'm coming to our results. So here you can see the selenium concentrations which we observed in these different chondrite groups and also from the differentiated planets. I also plotted some literature data for the CI group and for the bulk Earth and the mantle value. And what you can see is that we nicely reproduce the depletion trend of selenium when compared to the CI value. So we observe a depletion of selenium of up to a factor of 10. Then we measured the twilight phase, so the FES phase of the iron meteorites, which is enriched in selenium. That means that shows its siderophile character. And this is also the reason why selenium is depleted in the Earth's and the Martian mantle. The critical question is now, does this volatile-related depletion of selenium in the chondrites lead to an isotope fractionation? So do we see differences in the selenium isotope composition between the different chondrites? And does the selenium segregation into the metallic core leaving behind a mantle which is highly offset in selenium isotopes when we compare it to the chondrites? The answer to both questions is no. So these are the results for the selenium isotope composition of all our samples. Here you can again see the uncertainty of our method. And what we observe is that the chondrites are rather more homogeneous, so they plot at minus 0.17 plus minus 0.52 per mil. And this uncertainty is nearly the same as the uncertainty of our method. So we are not able to distinguish the different chondrites from the selenium isotope composition. If you now compare the values of the meteorites with that of the Earth, we just have one measurement so far, and this unfortunately had a very bad precision. But so far we cannot distinguish the Earth's mantle, which we measured by a sulfide melt, from the chondrites. So by now I can just say we cannot distinguish any sample which we measured so far for its selenium isotope composition. This leads us to the conclusion. What can we discuss about this? So there are in general 3 possible mechanisms to explain the very low, highly siderophile element abundances and also the selenium isotopes in the Earth's mantle. That is first core formation. Second is maybe an incomplete condensation from the solar nebula or a later evaporation of volatile elements on Earth. And the late process is the late veneer hypothesis, so maybe we had a delivery of a late accretionary component to the Earth. I will now just go quickly through these 3 processes and discuss what we could expect for selenium isotopes when these processes occur. First of all, from the core formation should leave behind mantle element concentrations which should be defined by their partition coefficient between the metal and the silicate phase. But what we observe is that the mantle concentrations of highly siderophile elements are higher than we would estimate it from the experiments. Furthermore, we observe that the chalcophile elements are even more depleted in the Earth's mantle than the highly siderophile elements. However, if you look at selenium isotopes, you would expect if we have a scavenging of selenium into the Earth's core that we have an isotope fractionation process at this process. We observe this for molybdenum or for silicon isotopes, for example. So there the core has a different isotope composition than the Earth's mantle. And so we would expect the same thing for selenium. So here you can see just a Rayleigh fractionation model. So here you can see the selenium isotopes on the y-axis as a function of how much of the selenium is going into the core. And from sulfur, we know, which is very similar to selenium, that about 97% of the sulfur is sitting in the Earth's core. So we would expect a similar thing for selenium. So we would expect if more or less all of the selenium is going into the Earth's core, that the Earth's mantle is highly enriched or depleted in selenium isotopes. But that's a thing that we don't observe. The second process is an incomplete condensation from the solar nebula or a later evaporation of volatile elements. This could be, for example, happen at the moon-forming impact. And here we can look at zinc isotopes because zinc has a very similar condensation temperature than selenium, so 726 degrees. But zinc is not siderophile as selenium, it's a lithophile element. If you look at zinc isotopes for the moon, for example, we observe that the moon is highly depleted in zinc and also has a very high or has very heavy zinc isotopes. If we then look for the zinc isotope composition for the Earth and the Mars, we observe that we cannot distinguish their values from the chondrite values. So from the zinc isotope, we would see that we have no clear indications that we have a volatile or evaporation loss of zinc from the Earth. Anyway, if this would occur for selenium isotopes, we would just expect that the selenium isotope composition of the mantle should be also offset from the chondrite value if a large portion of selenium is evaporated into space. The last process is the late Veneer hypothesis. The late Veneer hypothesis presumes that all highly siderophile elements are first completely segregated into the Earth's core, and that we have a late Veneer of a chondritic material. So from this, we would expect that the selenium isotope composition from the Earth's mantle should be the same as that from the late Veneer material. This leads us to the conclusion. So we observed that we have a homogeneous selenium isotope composition for the chondrites. This could be either explained by a complete condensation of selenium from the solar nebula, or that we don't have any significant selenium isotope fractionation during an evaporation or condensation process. So we will make more measurements of selenium isotopes in highly volatile depleted samples, so for example from the moon or from the moon. The second conclusion is that we cannot distinguish the selenium isotope composition from the chondrites from that of the Earth. This would argue either for a complete removal of selenium into the Earth's core, or that we don't have a significant selenium isotope composition during the segregation into the Earth's core. And this would be different to, for example, molybdenum or silicon isotopes. So from that, we need the isotope composition from the experiments, so from the melt silicate partitioning experiments. And the last conclusion is, if the core formation fractionates the selenium isotope, we would need a late Veneer of selenium to explain why the mantle has the same isotope composition than the chondrites. And with that, I would like to thank you for your attention.
Thank you very much. We have time for questions. Yes. Can you use the microphone, please?
If the chief source of selenium is the late Veneer, then what's your explanation for why the selenium abundance is less than that of the other highly siderophile elements?
That's not easy to explain. I mean, there are some complications with the late Veneer hypothesis. But if you look for example, selenium-tellurium ratios in the Earth's mantle, they have approximately chondritic ratios. So that would also argue for a late Veneer, because selenium and tellurium have different metal silicate partition coefficients. So you would expect from core formation that their concentration is different.
No, I understand that, but you also are going to need somehow to fractionate selenium from iridium, platinum, and so on.
Yeah. Maybe you have a combination of a late Veneer and a volatile loss, because these charcoal elements are more volatile than the platinum group elements. So this would argue that we must have an additional process which depletes even selenium and tellurium more than the platinum group elements. So maybe it's a volatile character of these elements.
We have time for one more question. Yes, they're in the back.
Actually, it's a comment. It's an answer to Mark's question. If you normalizing to CIs, they appear to be depleted compared to HSEs, but if you normalize to CVs, they set above. So you would solve that inconsistency.
Okay. Thank you.